Hello students, this is the fourth video on chapter 6 and it deals about the molecular structure. The learning objectives of this video is predict the structures of molecules using valence shell electron pair repulsion theory. As usual, I am going to explain today's topic, and I will explain by giving an example, and finally we will have some self-test activities. And what is the molecular structure? The molecular structure is arrangement of atoms in a molecule or ion, and you can predict the molecular structure by using formal charge or by using valence shell electron pair repulsion theory. How can you predict the molecular structure by using formal charge? First, calculate the formal charge for each atoms and then select the best Lewis structure. How can we identify the best Lewis structure? Go to the previous video and observe or watch the video. The main topic is predicting the valence shell electron pair, predicting the molecular structure using valence shell electron pair repulsion theory. What is the valence shell electron pair repulsion theory for us? The valence shell electron pair repulsion theory is a theory that predicts the shape and bond angles around the central atom of a molecule by moving the electron groups or pairs on a central atom as far apart as possible to minimize the mutual repulsion of the electrons. These electron groups are any type of bonds, may be single or double or triple, and maybe lone pairs of electrons. And what you are going to do is count the electron groups, that is lone pair, single, double or triple bond as one electron group as the central atom, and then determine its specific shape from the number of atoms bonded to the central atom. According to the valence shell electron pair repulsion theory, the order of electron group repulsion is this one. The repulsion between lone pair and lone pair is greater than the repulsion between the lone pair and the bond pair, and this is greater than the repulsion between bond pair and the bond pair. See this diagram. The lone pair repulsion is between this lone pair and this lone pair, and the lone pair bond pair repulsion is between this lone pair and this bond pair, or this lone pair and this bond pair, and the repulsion between bond pair and bond pair is the repulsion between this bond pair and this bond pair. And according to the valence shell electron pair repulsion theory, minimum repulsion occurs when the two electron groups are on opposite side of the central atom. This is the concept of valence shell electron pair repulsion theory. And there are two geometries. The first one is the electron pair geometry. The second one is the molecular geometry. What is the basic difference between these two? The difference is this one. The molecular geometry. The shape of molecule is determined by only the number of atoms that surround the central atom, but it does not consider the lone pairs, whereas the electron pair geometry is a geometry that considers both number of atoms and lone pair of electrons that surround the central atom. Remember always this, molecular geometry only considers the number of atoms that surround the central atom, but it ignores the lone pair, and the electron pair geometry considers both the number of atoms and number of lone pairs that surround the central atom. And we have two cases to determine the geometry of the molecule. The first one is when the central atom has the same number of electron groups as bonded atoms. The molecular geometry, in this case, the molecular geometry and the electron group geometry is the same. But in the second case, when the central atom has more electron group than the bonded atoms, the molecular geometry and the electron group geometry is different. Let me explain this with example. For the first case, where the number of atoms and the number of electron groups are the same. For example, consider this. If you draw the Lewis structure for this molecule, you can obtain this one. And the molecular geometry for this one is trigonal planar, and the electron pair geometry is similarly trigonal planar, because as you can see from this case, it says that when the central atom has the same number of electron groups, here the central atom carbon has the same number of electron groups, 1 electron group, 2 electron group, and 3 electron group. This double bond can be considered as 1 electron group. We have 3 electron groups here, and this is similar with the number of atoms that surround the central atom. We have 1, 2, 3 atoms, 2 hydrogen and 1 oxygen. So if there is equal number of the electron group and equal number of atoms that surround the central atom, and then the molecular geometry and the electron pair geometry is the same. So in this case, both electron group geometry and molecular electron pair geometry and molecular geometry is trigonal planar. Another example for this case is this one. When you draw the Lewis structure for this, you can get this one. This is the Lewis structure. So how many atoms surround the central atom? There are 4 hydrogen atoms that surround the central atom. And then how many electron groups that surround the central atom? We have also 4 electron groups. This single bond, this single bond, and this single bond, this single bond. We have 4 electron groups. So the molecular geometry and the electron pair geometry is similar. And the answer is tetrahedral for molecular geometry and tetrahedral for electron pair, electron group geometry, or electron pair group geometry. So this is one case. The second case is when the central atom has more electron group than bonded atoms. For example, consider sulfur dioxide. If you draw the Lewis structure for sulfur dioxide, you will get this one. And how many atoms surround the sulfur? We have 2 atoms, this oxygen and this oxygen. But how many electron groups surround the sulfur atom? We have 3 electron groups. That is more than the atoms. 1 electron group, 2 electron group, and 3 electron group. Count the double bond as a single electron group. We have 3 electron groups and 2 atoms that surround the central atom. So in this case, the molecular geometry and the electron pair geometry is different. And the molecular geometry is bent, and the electron pair geometry is trigonal planar. This is one example. Another example is for ammonia. If you draw the electron Lewis structure for ammonia, you will get this. How many atoms surround the central atom nitrogen? 1, 2, 3 hydrogen atoms surround. How many electron groups surround? 1 lone pair, 2, 3, 4. So there is different naming of the geometry. Then the molecular geometry is the trigonal bipyramidal, whereas the electron pair geometry is tetrahedral. So this is the way of identifying the molecular and the electron pair geometry. And generally, classification for electron molecular geometry, we have 5 basic electron molecular geometries. Let me explain this with simulation. If the central atom has no any lone pair, that molecular geometry is considered as basic molecular geometry, and we have 5 basic molecular geometries. The first one is if the central atom is surrounded by 2 atoms, and if there is no lone pair at the central atom, this molecular geometry is considered as linear. Example, the beryllium chloride. Then the angle between these two is 180 degree. And if the if the central atom is surrounded by 3 atoms, and if there is no lone pair at the central atom, this molecular geometry is considered as trigonal planar. Example, boron trifluoride. Another thing is if the central atom is surrounded by 4 atoms, and if there is no lone pair as the central atom, this geometry is called tetrahedral. Example, you can take this methane. Another fourth molecular geometry is trigonal bipyramid. If a molecule is surrounded by 5 atoms and if there is no lone pair as the central atom, such type of geometry is called trigonal bipyramidal. Example, phosphorus pentachloride. And the fifth basic geometry is octahedral. If the central atom is surrounded by 6 atoms and if there is no lone pair as the central atom, such type of geometry is called octahedral. Example, sulfur trifluoride. And these are the 5 basic molecular geometries when if there is no lone pair as the central atom. Another thing is, what about if the central atom has lone pair? We have examples here. This is the first case when the central atom is surrounded by 2 atoms and if there is no lone pair as a central atom, this is linear. You can consider these examples. And another is this one. If the central atom is surrounded by 3 electron groups, if all bonding atoms are, if there is no lone pair as the central atom, and if the central atom is surrounded by the 3 atoms, such type of the arrangement is called the trigonal planar. Example, sulfur trioxide, boron trifluoride, and nitrate ion. You can consider this. But if the central atom is surrounded by 2 atoms and if there is one lone pair as a central atom, and this type of the molecular structure is called bent or V-shaped. Example, you can take or you can consider these examples. Another geometry is a geometry or a central atom with 4 electron groups. You may obtain AX4 form or AX3E form or AX2E2 form. This case is if the central atom is surrounded by 4 atoms and if there is no lone pair as a central atom, such type of molecule is called the tetrahedral molecule. But if the central atom is surrounded by the 3 atoms and if there is one lone pair as a central atom, such type of molecule is considered as trigonal bipyramidal molecule. Example, you can take these examples. If a central atom is surrounded by 2 atoms and if there is 2 lone pair as a central atom, this type of molecule is considered as bent or V-shaped. This is one case. Another case is if the central atom is surrounded by 5 electron groups. We have again 3 cases in this case. The first case is if the central atom is surrounded by 5 atoms and if there is no lone pair as a central atom, this shape is a trigonal bipyramidal shape. Take example this. And if a central atom is surrounded by 4 atoms and if there is one lone pair as a central atom, this is seesaw shape. Example, you can take this example. And if a central atom is surrounded by 3 atoms and if there are 2 lone pairs as a central atom, this shape is T-shaped. You can take this example. And the fourth one, if the central atom is surrounded by 2 atoms and 3 lone pairs, E is lone pair, and this shape is considered as linear shape. You can take this example. This is one case. And the last molecular geometry is if the central atom is surrounded by 6 electron groups. We have again 3 cases in this case. One case is if a central atom is surrounded by 6 atoms and if there is no lone pair at the central atom, the shape is octahedral shape. Example, sulfur trioxide, and you can take this example. The second case is if a central atom A is surrounded by 5 atoms and if there is one lone pair as central atom, the shape is square bipyramidal. Example, this one. And the third one is if a central atom is surrounded by 4 atoms and if there are 2 lone pairs as a central atom, and the shape is square planar shape. You can take these examples. This is the molecular geometry, all about the molecular geometry, and let me explain this with simulation. Consider this this molecule, the water molecule, and the molecular geometry is bent and the electron geometry is tetrahedral, because the molecular geometry only considers the atoms that surround the central atom. We have 2 atoms, and the electron geometry considers the lone pair also. We have 4 electron groups that surround the central atom, 2 lone pairs and 2 atoms. So we have this, the electron geometry is tetrahedral, but the molecular geometry is bent. Another example is the carbon dioxide. The molecular geometry is linear and the electron geometry is linear because the number of atoms that surround central atom and the electron groups that surround the central atom is equal. We have 2 number of atoms that surround the central atom and we have 2 electron groups, 1 electron group here, 1 electron group here. So there are equal number of electron groups and number of atoms that surround the central atom, and the molecular geometry and electron pair geometry is similar. And another example is for sulfur dioxide. The molecular geometry and electron pair geometry is different because the number of the electron groups that surround the central atom and the number of atoms that surround the central atom are different. Here we have 2 atoms that surround the central atom, and we have 1, 2, 3 electron groups that surround central atom. So there is different numbers. And another is for this one. For this, the electron group geometry is trigonal bipyramidal and the molecular geometry is linear because there are 1, 2, 3, 4, 5 surrounding electron groups. So that is trigonal bipyramid, but 2 atoms surrounding, the molecular geometry is linear, and so on. We can see for this, you can see molecular geometry and electron geometry. You can see again for this one, the angle and the molecular and the electron geometry. You can observe this one. Another is for ammonia. You can see the molecular geometry is trigonal bipyramidal and the electron geometry is tetrahedral. And the like for this molecule, you can again consider the molecular geometry and electron geometry and the like. So this is all about today's lesson. The next video or self-test draw the Lewis structure and predict the shape for each of the following molecules. Do by yourself. And the next video is this one, that is polarity of bonds and polarity of molecules. Thank you for watching this video. See you next time. Bye bye.